Okay, let's jump right into this. Welcome, 7th graders, to today's explainer for Unit 06, Lesson 1. Today is all about problem solving and computational thinking. Now, I know what you're probably thinking. You hear computational thinking, and you instantly picture like some hacker furiously typing complex code on a dark screen, right? Actually, scratch that. That's not what this is about at all. Computational thinking is really just a universal problem-solving toolkit. It's a structured way of looking at the world that puts you completely in the driver's seat when it comes to technology. Basically, we're going to learn how to think like a computer so we can command them to do all the heavy lifting for us. Let's get into it. So here's our visual roadmap for today. First, a welcome to problem solving, then decomposition, abstraction, and patterns, designing your algorithms, and finally, your big application task.
All right, part 1, welcome to problem solving.
At its absolute core, technology isn't just about flashy screens or mind-blowing video games. It's fundamentally about solving real-world problems. Whether we're, trying to predict the weather, designing a fair game, or building an app to help our neighborhood, we're acting as problem solvers. I actually love this quote directly from the computer science standards: address complex problems as algorithms. So what does this actually mean for us? It means that when we face a massive, overwhelming issue, we don't just guess. We literally never just start mashing keys on a keyboard hoping for the best. Instead, we use structured computational thinking to design a careful, step-by-step solution. We plan before we build, always.
Moving on to part 2, decomposition, or breaking it down.
So, when a problem is just way too big for a single person to solve, or even for a computer to process all at once, the absolute best way to handle that massive beast of a task is to rip it into smaller, bite-sized pieces. Formally, decomposition is defined as breaking down problems and subproblems into smaller parts to facilitate design, implementation, and review. And honestly, this is a real game changer. Why? Because when you break a problem down, it means different students can work on different parts of a project at the exact same time without stepping on each other's toes.
And this slide brilliantly illustrates how it works in the real world. Imagine your task is creating an entire animated movie from scratch. If you look at that as one giant, single task, well, it's terrifying, right? It's just way too complex. But look at the decomposed parts. Instead of panicking over the whole shebang, you just focus on one specific thing at a time. First, maybe selecting the backgrounds, then placing the characters, finally programming their specific actions. You could even hand one scene off to a friend while you work on another. By breaking it down, the impossible suddenly becomes totally doable.
Okay, part 3, abstraction and patterns. Let's talk about working efficiently.
Once we've broken our massive problems down, we need to be really smart about how we actually solve those smaller pieces. Abstraction is defined as creating generalized procedures with parameters to organize code and make it easier to reuse. What does that mean in plain English? Well, it means we don't want to write the same instructions over and over again. As programmers, we want to be efficient, maybe even a little bit creatively lazy. So we hide the super complicated details behind a single, easily reusable command. Here is a perfect example of abstraction in action. Think about drawing a circle on a screen. Under the hood, it actually requires dozens of tiny, complicated mathematical instructions. But instead of writing out 100 lines of math every single time you want a shape, you just use a generalized draw circle procedure. But just plugging in a size parameter, like the radius, you can use that exact same piece of code to get a tiny dot, a medium wheel, or a giant hoop. See? You've abstracted all those messy details away.
Now, right alongside abstraction comes pattern recognition, which is absolutely vital when we're refining our computational models. A computational model is basically a program that makes predictions based on data. But here's the secret. Models are rarely perfect right out of the gate. We have to refine them. We do this by looking really closely at our data, spotting patterns, and testing our predictions against actual real-world results to see which variables really make a difference.
Let's apply this to a real scenario. Imagine you're programming a physics simulation to predict how far a ball is going to travel off a ramp. Now, to make that simulation accurate, you can't just program a generic, boring ball. You have to identify patterns and relationships between specific inputs. As you can see on the slide, you have to track the height of the ramp, the angle of the track, the size of the ball, and the mass of the ball. If your virtual ball travels way too far compared to a real one, well, you look at your variables, recognize where the pattern is breaking down, and tweak your code.
All right, part 4, designing your algorithms. Time to map out the solution.
So we've broken our problem down and we found some efficient patterns. Now we finally get to map out our complete solution. An algorithm is, quite simply, a precise sequence of instructions. But before we even think about touching a programming language like Python or JavaScript, we have to design that algorithm. We use cool tools like visual flowcharts and pseudocode, which, if you don't know, is kind of like a half-English, half-code secret language. We use these to logically organize and sequence our steps. We map it all out visually before typing a single line of actual code. Take this mini narrative of a sneaker buyer, for example. If you want to build an app that recommends the absolute perfect pair of shoes, your algorithm needs a really clear flow. Step 1. You take in a wide range of user inputs, right? Their shoe size, favorite color, brand preference, comfort needs, and of course their budget. Step 2. Your algorithm processes all that data, maybe using those conditional statements and patterns we just talked about. And step 3, it spits out a perfect automated sneaker recommendation. Testing this entire algorithm on paper with flowcharts first ensures you haven't forgotten any crucial steps before you go through the hassle of building the real app.
And finally, part 5, your application task. Time to apply what you've learned. All right, 7th graders, huge congratulations on grasping the 4 main pillars today: decomposing problems, abstracting details, recognizing patterns, and designing algorithms. Now it is time to apply everything you've just learned. For your assignment, you are going to design your very own algorithm to address a complex problem, creating your own flowcharts and pseudocode. But here is the real challenge. Your design must include nested loops, which remember are just loops placed inside of other loops, and compound conditionals. Compound conditionals just mean you are combining logic. You'll be using terms like and, or, and not to tightly control exactly what happens in your program based on multiple rules all firing at once.
To help you visualize this, let's look at this specific interactive story example from our source material. Imagine you're programming a video game, and you want to use a compound conditional to enforce the rules of the game. So, in your pseudocode, you'd write a rule that says something like, unlock a door only if a character has a key and is touching the door. Both of those conditions must be totally true for the action to trigger. That is the magic power of AND logic. This is exactly the kind of structured, step-by-step logic you're going to be demonstrating in your application task. So, what does this all mean? The crucial point here is that computational thinking isn't really just about computers. It's about empowering you to take any massive, messy, real-world problem and confidently engineer a brilliant solution. You now have the exact toolkit you need. You know how to break things down, spot the patterns, and visually map your logic. So I'll leave you with this final thought for the day. What complex problem will your algorithm solve today? Good luck on your transfer task, everyone. I absolutely can't wait to see the incredible algorithms you design.